We will see now a consequence of Holder inequality. And the consequence is that one can see any space LP inside the dual of LP star, where P star is the exponent conjugated to P. So let's state the result. Let's P and Q in 1 infinity with 1 in infinity included. So conjugate exponents. And we need to assume that mu is sigma finite in the case we are considering P equal to infinity. Otherwise, it's not necessary. Then we have the function, let's call it phi from LP to the dual of LQ, defined as for any f, we consider the map, let's call it phi of s, phi sub f, defined as phi sub f applied to an element g in LP is the integral of fg in d mu. This should be similar to what we're doing in the case of Hilbert space, considering the scalar product. But now we're taking some kind of strange scalar product between an element in LP and an element in LQ. Okay, so the statement is this function is a linear map, continuous, and is actually an isometric embedding. So it might not be surjective. Actually, we will go back to the point of surjectivity, but it preserves the norm of vectors. Okay, so this is the corollary that we are going to prove now. And as I said, it's based on Holder's inequality. So by Holder's inequality, so what we have that phi sub f of g, the norm, this is less than of the p norm of f times the q norm of g. So what we get is that phi f is, okay, it should be also clear that it's linear in G, and what we have that is a bounded operator. Okay, and the norm is actually bounded by the norm of f. So the map f goes to phi of f. This map is, okay, it's also linear in f. It's linear, it's trivial, but it's also one Lipschitz. Same, so again, this Holder inequality tells us that the operator norm of phi of f as an element in LQ star, this is bounded by the norm of f in LP. Okay, now what we want to prove is that we actually have equality. So we will need to find a good G to show that for some G this becomes an equality. Okay, but to do that we have to separate the three cases according to the exponents. So first case, we consider P different than 1 and different than infinity. Okay, so to see that the norm is not decreased, we consider the function g to be the sine of sine of f. So it's +1 if f is positive and -1 if f is negative. Sine of f, f to the p over q. Okay, so let's consider this function. Okay, first let's check that this function is in LP. So notice that. Okay, let's consider the q power of the q norm of g. Right? So this is the integral of g to the q, the mu. Okay, we put the definition of g, and of course this is going to be f of p, the mu, which is the p norm, p power of the p norm of f, which is finite. Okay, so g is in LQ. Okay, now let's see how the evaluation of the map phi behaves in G. What we have that phi f g, this is, okay, by definition is the integral of fg. Now let's put the definition of g, so it's sine of f times norm of f to the p over q, the mu. And now this is equal to is the sum of f, is the integral of f to the power p over q plus 1 the mu. Now the fact that we have the exponents are conjugated, this quantity is equal to p. Okay, and this becomes the p norm of f. So see, g does not decrease the norm. Phi does not decrease the norm of g. So phi f preserves the norm of g. Okay, so phi f is phi is an isometric embedding. Good. Okay, this was for the case of p different than 1 and infinity. Let's consider the second case when p is 1 and therefore q is infinity. Now in this case we take g to be just the sine of f, which is a bounded function, bounded by 1, and the norm and the essential soup is 1. Okay, what we have for this function, we have that if you consider phi f g, this is equal to sine of f times f. This becomes the absolute value of f, which is equal to the 1 norm of f. So same thing for g. So this g is preserved in norm. Okay. Third and last case, case in which p is equal to infinity and therefore q is equal to 1. Now it's a little bit more tricky, and so we need to use the sigma finite. So mu is sigma finite. This will imply that for any n natural number, there exists some measurable set such that the measure of this set is non-zero and it's finite, and f x in norm is greater than the absolute the essential soup minus 1 over n for all x in a n. Now if this we consider Gn to be the function 1 over the measure of n, an characteristic of an, times the sign of f. So as you see, this is when you take the norm, the absolute value, this disappears, and this is exactly an average. So the function Gn is in L1 with one norm to be equal to 1. And what is now phi f applies to Gn is 1 over the measure of an, the integral over an of f times the sign of f. Again, it becomes the norm of f, the mu. And on an, we have the bound that the absolute value is slightly bigger, so slightly smaller than the essential sup. So this is, we can bound this as, since it's an average integral, f of infinity minus 1 over n. And this is for any n. In the limit, we get that the norm of this quantity is at least the norm of f. So what we also get is that, again, the norm phi f is equal to the infinity norm of f. And this concludes the proof of the inclusion of LP inside the dual of LQ. So fixed a measure space, we have been considering these LP spaces when P is this exponent that varies between 1 and infinity, including infinity. And these families, in general, they're not related to each other, but we could say something, for example, when the measure is finite, or when we consider more than one exponent, in the following way. So the first theorem I want to present is the fact that if the measure of the whole space is finite, then we have an inclusion. Then whenever you have exponents p and q with p less than q, between 1 and infinity, including the extremes, then the LP spaces reverse the inclusion. So the order. LP now contains LQ. Okay, let's prove this. So, okay, let's consider first the case Q different than infinity. So also P is less than infinity. Okay, and now I want you to notice that, so if you have two numbers, P less than Q, then, so if you have a value T greater than 1, so for T greater than 1, taking the power to P and Q is preserve the order. T to the Q is less or equal than T to the Q. Instead, if T is in between 0 and 1, then taking, okay, the inequality gets reversed, but let's not consider that. Let's consider the fact that T to the P still stays less than 1. So in conclusion, what we can say for all positive T's, T to the P can be bounded by T to the Q plus 1. Okay, so now let's use this bound. So then, if you have the integral, if you want to consider so what we are doing, we're taking an element in LQ and show that it's in LP. So F will be an element with finite Q norm. Let's bound now the LP norm. So the LP, or the P power of the LP norm, this can be, so this is, norm of F is a positive number, so it's less than the integral of F to the q plus 1 d mu. Okay, but now we can integrate one term at a time. In the first is going to be the q power of the q norm of f plus the integral of 1 over the whole space. So it's the measure of E. And we assume that if these two are bounded, then also the p power of f is bounded. So the inclusion is proved in this case, the case q less than infinity. Now the second case, p equal to infinity, q equal to infinity. And of course, p is enough to consider different. So p is less than infinity. So what we have that if you take a function f, then of course its absolute value is less or equal than the essential sup of f. This is true almost everywhere by definition of the essential sup. And therefore, if we integrate the p power is less or equal than the integral of the infinity norm. But now this is just a number integrating on the whole space E. So what we get is, okay, I forgot the power p. So this is the norm, the infinity norm of p times the measure E of E, which we are assuming is finite. This is the proof of the first containment I want to show. I will now explain another containment without any assumption on finiteness of the measure. And this is the following theorem. So suppose you have p and q, again, with p less than q, considering also the case of infinity. Now, the question is, what happens if I take LP and intersect with LQ? And what I want to prove is that this is contained in L, another exponents call it R, for all R that are in between P and Q. So in this interval. So this is what we're going to do. Proof. Okay. Again, we have to consider the different cases, finite Q and infinite Q. So if Q is different than infinity, now, okay, let's take F in LP intersect LQ. And of course, when I say this, I'm going to, I mean, take a representative of the element of a class. So a representative of an element in LP intersect LQ. So now, therefore, we can, now we do the splitting. It's important to have it f defined as a function at every point. So we split f as g plus h with the following way. G is going to be f when f is greater than 1. And g and 0 otherwise. G is going to be f when f is smaller than 1 and 0 otherwise. Okay, so at every point, either f or g is positive, so it's different than 0. So what we get is that f, the absolute value of f is equal to the absolute value of g plus the absolute value of h. Okay, now notice, so we're going to bound differently g and h, because if you have a number t that is greater than 1, then what we have is that t to the r is smaller or equal than t to the q, right? Because r is smaller than q. For positive, for greater than 1, it preserves the same order. If instead t is in between 0 and 1, then we have the opposite inequality, so we use t to the r less than t to the p, because now p is less than r. Okay, we are going to use this two inequality to bound the norm of f to the r. So what we get, so we get that fx power of r, if it's greater than 1, we bound it with g to the power q. If it's between 0 and 1, we bound it with h to the power p. Okay, now we integrate. And what we get, we integrate f power r mu. This is less or equal the integral of g, so we get the g power, the q power of the norm of g, plus the h, the p power of the norm of h. But g and f are smaller than f, so the first one can be bounded by the norm of f q power plus the norm of f in p power. Okay, now this is finite. So this is the case where q was finite. The last case is when q is equal to infinity and p is less than r is less than infinity. Okay, in this case we have norm of f to the r. We can write it as norm of f r minus p times norm of f to the p. And now norm of the absolute value of f can be bounded by the essential sup of f times f to the p. Now we integrate, and we get that the r power of the r norm of f is less than, so integrated we get the essential sup of f to the power r minus p times the p power of the norm of p norm of f, which is finite. In all cases, we prove that as soon as the p and q norms are finite, then the r norm is finite. So every f is in LR. This ends the proof. The LP spaces are big spaces because you have many possible functions. But there are some theorems that tells us that some smaller class of a smaller subset of these LP spaces are dense in these spaces. And these theorems are useful because maybe instead of proving something for every element in LP, then it's easier to prove for this subclass and then show that the property pass to limits. So there are several density theorems. I will present two theorems and I will explain the proof, but without too many details. So the first theorem that I'll present is for all p greater than 1, but not p equal to infinity. What we have is that the space of step functions, namely you consider sum of ak, characteristic of ak, from summing from k from 1 to n, where n is a natural number. Ak, they are reals, not only positive, they're reals, and ak are sets in the sigma algebra with finite measure. This is for all k. Okay. So this space of functions is dense in LP. Okay. So also notice, and I will prove it, but notice that this set here is a vector space. So you can add two functions of this type and stays of this type. So what we have in infinite dimensions, we have a sub vector space of a vector space that is dense, but is not everything. This does not happen in finite dimensions. So, and it is a linear space or linear subspace that is not closed. Not closed. Because the closure is all of LP. Okay. I will go back to this theorem. But the second theorem is, suppose you have a, I would say, proper metric space, but more generally, one can consider, okay, let's stay, okay, locally compact Hausdorff topological space, mu Borel regular measure on E, finite on compact sets, then for all p greater than 1, with p different than infinity, the space, we call it C0 CE of compactly supported continuous functions is dense in LP. Okay, apart from the density, again, observe that, okay, it's easy to show that these functions, since are compactly supported and therefore bounded, they are obviously in LP. And also notice that again, this is a vector space, infinite dimensional vector space, which then is going to be dense in this vector space, but not closed. Before remarking something about the validity of these two theorems, let me remark that this is not true for p equal to infinity, neither of the two theorems. And one can think of, for example, on R, if you have the function constantly equal to 1, this is of course, okay, no, we cannot take this because as we required constant finite measure. Okay, let's see what could be an example showing that these two are not true for LP. Right. The function constantly equal to 1, it's in L infinity because the essential sup is 1, but it cannot be approximated with a constantly supported function because the sup of the difference is going to be outside the compact set where we take outside the support of the function, the difference is going to be 1. So the sup distance between any element in C infinity C is going to be 1 with the constant function that on R is constantly equal to 1. So I'll remark that so the same, it is not true, is not true for p equal to infinity. And actually what we can say is that the closure of C0 compactly supported E in L infinity, it is an interesting set, and this is the space, of functions, let me say, that vanish at infinity, which means that f is such that for all epsilon there exists a compact set outside of which, if we consider the complement function, the function of the complement, then the absolute value of this function is less than epsilon. So outside a compact set, they are arbitrarily small. So this is the closure. In particular, this is not everything. Okay, let me say something about the proof of these two theorems without too many details. So to prove that the step functions are dense in LP, actually we more or less saw this for L1, or actually maybe this was the way we were defining integrable functions as limits of step functions. But the idea is the following: we take f in LP, and now think of the graph of the function. Now what we do, we cut the range in small pieces, and what we do, we perturb the function considering the lower level of the function. So in formula is the following. So for all n, we consider fn to be the sum of, so we are dividing into 2 to the n in strips of 2 to the n, and so we go from k from 0 to 4 to the n, and this is the characteristic of k of the set where f is between k 2 to the n and k plus 1 2 to the n. Okay, so we cut the function, and now what we have is that this function is always less than f and pointwise converges to f, and this is an element, this is a step function which converges to f almost everywhere, and because of the dominated convergence theorem, the LP norm also between these two, of the difference of these two functions, goes to 0. So this is quickly why the density of the step functions in LP is true. Regarding the continuity, regarding the case of continuous compactly supported function, one notice that, okay, we can, to prove the density for the space of LP, since we know already that step functions are dense, it's enough to approximate now step functions with continuously supported function. But now if we have a compactly supported, if you have a so we have the case of f equal to the characteristic of a set with the measure of the set being finite. Okay, so it's enough to prove that we can approximate these functions here with the continuously supported function. But now what we do, we use two things. We use the fact that the measure is Borel regular, so we can approximate A with compact sets, and we use the Urison lemma that say that we can approximate the characteristic of a compact set with continuously supported functions. So in brief, so a regularity plus Urison tells us that C0 functions approximate the characteristic of any set of finite measure. Okay, this is in brief the two density theorems that I wanted to discuss.